Again, it's on the FMBR website. Now let me introduce Dr. Robert Lustig, who is currently Professor of Clinical Pediatrics in the Division of Endocrinology at UCSF and Director of the Weight Assessment for Teen and Child Health Watch program at UCSF. He's a neuroendocrinologist with basic and clinical training relative to the hypothalamic development, anatomy, and function. He worked at St. Jude's Hospital, and he's a native of Brooklyn, my hometown. He went to Stuyvesant, received his MD from Cornell, and pediatric residency at St. Louis Children's Hospital. Let me go on. He's authored 60 peer-reviewed articles and 30 reviews. He has mentored 15 pediatric endocrine fellows and trained numerous other allied health professionals. He provides endocrinology support to several protocols of the Children's Oncology Group. He's currently chairman of the ad hoc Obesity Task Force of the Lawson-Wilkins Pediatric Endocrine Society. And lives in San Francisco, and let me introduce Robert Lustig.
Thank you, Mr. Burke. Dr. Thank you all for coming tonight. Can I just get a show of hands? How many of you are physicians? Not too many. Okay. There's a lot of biochemical data. After listening to the first hour here, I've come to the realization that you're a bunch of naysayers, which is real good, okay, in terms of skepticism. And so in order to be able to prove my point, I'm going to have to show you a lot of data, okay, where you're all going to say, what does he know? So there are quite a few slides. It's going to be a relatively long talk. I'm going to make a suggestion that we actually have a break. There's a natural break. There's an intermission. Maybe we can have like a 3-minute intermission to stretch your legs in the middle, okay, just to sort of, get our act back together again. And then we'll go on. That's all right with everyone, okay? In addition, because the newsletter that was sent out to all of you has a lot of the information that's on the slides, some of the things I'm going to cycle through pretty fast, okay? Where I think we, non-MDs need further education, I'll certainly stop and spend more time, okay? So we'll try to do this best we can, okay? All right. It's very sad when the tabloids are the oracles of our society, okay? When they can predict the future. In fact, this was from 1993, and I now have patients that look like this. Sadly. Okay? If you look at the BMI distribution, everybody know what BMI is? Body mass index, weight per height. Okay? You can see that there's a slow, steady march to the right. Okay, here was the NHANES, the National Health and Nutrition Examination Surveys, from 1988 and then in 99-2000, and here's the one projected for 2008. Okay, and actually we're on target to actually surpass that. Okay. The point I want to make on this slide is that the entire curve has shifted. It's not just that the obese are getting obese-er. That's true. But so is everyone. In fact, everyone in America weighs 25 pounds more today than they did 20 years ago. So whatever's happened, the average person, the average human being in America, okay, weighs 25 pounds more today than they did 20 years ago. Okay? Everyone. So whatever's happening is happening to everyone. Now, of course, everyone makes a big deal about obesity being, an interaction between genetics and environment. But the fact of the matter is, genetics haven't changed in 30 years, but God knows our environment sure has. And that has a lot to do with what we're going to talk about today. It's what's happened to our environment. Okay? We're going to go through that. And this is just children data, for those of you, since a lot of you are here, interested in aging. Okay? Aging starts in childhood, if you didn't know. Okay? It doesn't matter if you're prepubertal or pubertal. It doesn't matter if you're black or white. It doesn't matter if you're male or female. The prevalence of obesity is going up in every single group. Okay? Particularly the adolescent black female. We can talk about why that is in a little while. Okay? It's pretty bad. So, you all are, physicists. You all understand the first law of thermodynamics, right? Which states that the total energy inside a closed system remains constant. In human terms, the standard interpretation is the following. If you eat it, you better burn it, or you're in a store. Now, who here believes that? Oh, come on. Okay. In fact, you really all believe that. Okay? But why do you believe it? Makes sense, right?
Right.
Sure. Okay. I used to believe it. I don't believe it anymore. Okay? I've changed my mind. I think that's a crock of fool. Okay? And it's what's wrong with what's going on in America today. And I'm going to try to explain in the first part of the talk why I think that's a crock of fool. But if you do believe it, then, after all, weight gain is then secondary to increased caloric intake, in other words, eating, which is a behavior, and decreased energy expenditure or physical activity, which is a behavior. Therefore, weight gain or obesity is secondary to a group of behaviors. Therefore, we can call that personal responsibility. Okay? And Dr. Miller introduced the concept of personal responsibility, although he was talking about financial personal responsibility. I'm talking about ethical personal responsibility here. Okay? And in fact, this works for the government to propose this, because if it were anything else, they'd have to pay for it. In fact, they don't have to pay for it if it's a behavior, do they? Because they can say, that's your fault. Right? You're fat? Go fix it yourself. Okay? I don't believe that's right. And in fact, I'll prove it to you. That's what this is all about. Okay? What is the definition of the behavior? Here it is right here. A stereotyped motor response to a physiological stimulus. So let's take that apart. Stereotype. Same each time. So yes, eating is a behavior because it looks the same from the outside every time you do it. Motor. Muscles have to move. A thought is not a behavior. Or Jimmy Carter would be in hell. Just a joke. Okay? And finally, physiological. And so that's what I really want to know. I would like to know, what is the physiological basis behind gluttony and sloth? Now, maybe there are some adults out there who actually choose to be obese. That's actually a choice they make. Okay? Rossini, the famous composer, Barber of Seville, La Gazza Ladra, and all those. Okay? He retired at age 37 to live a life of gastronomic debauchery. Okay? So maybe he chose to be obese. I'll give you Rossini there, okay? Okay? But no child chooses to be obese. Okay? Obese children have a quality of life the same as kids on cancer chemotherapy. They are ostracized from their peers. They don't play with other kids. In fact, it's even worse today than it was 40 years ago when these studies were originally done. They've actually redone them. It's actually worse. The pejorativeness of it. Okay? They feel like crap. They don't do well in school. It's a complete and utter disaster. No child chooses to be obese. Okay? I am a pediatrician, and I'm here to tell you that that is just a crock of garbage. No child chooses to be obese. And in fact, the group that's got the greatest increase in prevalence in obesity is the 2 to 5-year-old, who are incapable of accepting personal responsibility. So how can you make obesity personal responsibility? If anything, the exception proves the rule. So how do you explain all this? Sorry?
Blame.
Blame. Oh, yeah, well, it's very easy, isn't it? Okay, well, let's get past the blame now. If it were a behavior, then a behavioral modification should fix it, shouldn't it? Okay? Well, this is a tome on the internet. You can pull this up. Okay? Here's the website right up here. This is written by my colleagues from the Center for Weight and Health at UC Berkeley. Okay? And it's called Pediatric Overweight, a Review of the Literature. And it's a meta-analysis of all of the obesity studies done in children for the last 20 years. Okay? And I'm just going to read you one paragraph. It's the summary of how well diet and physical activity interventions work in children. Okay? Primary prevention of overweight in children should begin at early ages. Parents are particularly effective agents for change in the health habits of children and should be incorporated into prevention interventions. So far, no problem. It's recommended that interventions be interdisciplinary, sustainable, and of long duration. Okay? Pediatric prevention interventions should target improving health without primary emphasis on body size or fatness. Still okay. Okay, here's the kicker. This is the big one. Many interventions show success in knowledge and reported behaviors, but little effect on BMI or prevalence of overweight, most notably the large and expensive catch and pathways trials. Doesn't work. Doesn't work. In fact, if it worked, you wouldn't have invited me. Okay? You know it doesn't work. It's all around you. And it doesn't work. Why doesn't it work? Maybe it's because that interpretation of the first law is the problem. So let's talk about that. Okay? In order to talk about it, we have to talk about a different phenomenon. Not obesity, we have to talk about a different phenomenon. It's called starvation. Because ultimately, I'm going to prove to you that obesity and starvation are actually one and the same. Okay? And you'll see how. We're going to talk about a phenomenon called leptin resistance. Okay? Everybody read the newsletter? Everybody know what leptin is now? Because we can cycle through this stuff relatively quickly if we can. Okay? I'm going to show you both rat and human data, and ultimately, what you have to know is this is all about an area of the brain called the hypothalamus, which controls all the hormonal systems of the body. And the hypothalamus is right up here, this little pink thing up here called VMH, ventromedial hypothalamus. You'll notice that there are 4 hormones feeding that VMH, and they're in blue. Okay? There are 2 GI hormones. One's called ghrelin, comes from the stomach. That's the hunger hormone. That's the hormone that tells your brain you're hungry. When your stomach's empty, your ghrelin goes up. When you eat something, it goes down. Okay, so that's the hunger hormone. Over here we have another hormone that comes from your small intestine called PYY 3 to 36, peptide YY. This is the hormone that basically tells you not to go back for thirds at the Indian buffet. This is the satiety hormone. Okay? This is the hormone that it's located at the end of the distal intestine. If it were at the beginning of the intestine, we wouldn't have a problem, but it's at the end. You have 22 feet of intestine that the food has to actually get through before you can signal this to your brain. Okay? That takes time. Okay? So, kid sits down, eats an entire plate of food, says to the mom, I'm still hungry. And the mom looks at him incredulous. How can you be hungry? You just ate a whole plate of food. That's why he's hungry. Because the PYY signal hasn't been generated yet. Okay? That's why. So the kid is still hungry, but he won't be in 20 minutes. So that's one of the problems, is immediate gratification with a second portion. And that's one of the things we teach in our clinic, is try to not allow that to happen. Okay? To try to limit portions to 1 portion rather than 2 portions. Okay? Slower eating, too. Absolutely. Didn't your mom tell you to chew your food?
Yeah.
That's why. Every mom's a dietitian, didn't you know? Right. And then we have these other 2 hormones over here. One's called leptin. Okay, it comes from the adipocytes. Tells your brain not how fat you are. That's the fallacy. It tells your brain how thin you are. Each of us has a personal leptin threshold. Okay, it's probably genetically determined. Okay, so let's take Dr. Miller here. Nice thin guy. I'm so jealous. Okay, let's say his personal leptin threshold is 20. Okay, so if his leptin's 20, or 21, or 22, okay, or 53, so he's getting fatter as the leptin goes up, because it's a marker for how much body fat you have. Okay? Or 186 for that matter. Okay? It's all the same to his hypothalamus. It's above 20. And therefore, his brain is going to interpret that 20 as being energy sufficient. He is going to burn energy at a normal rate. And I'll show you that on the slide. Okay? Let's say Dr. Miller decides to go on a diet. Not that he needs to, but let's say he does. And his leptin level drops to 19. He is now below his personal leptin threshold. What's his brain going to see? It's going to see energy insufficiency. It's going to see starvation. So then the question is, what happens when you're starved? I'm going to show you. Okay? So that's what we're going to talk about today. To get into this, let me just show you a couple of drug studies, since Dr. Miller really picked on them. and I actually agree with you on some of that. This was the original Redux study. Everybody remember Redux? Got pulled in 1997 for cardiac valvulopathy. Okay? But what I want you to notice is, notice there's a nice weight loss here, but then you hit the 4-month time point, and that's the end. No more. How come? Did the patient stop taking it? Did it stop working? If you look at the food intake data, it was still down. So how come they stopped losing? If you're right about the first law, then decreased energy intake should result in weight loss, shouldn't it? But it doesn't. Here's sibutramine, or Meridian. It's out on the market right now. 4 months, that's it, done, finished, no more. And here's more or less that, the fat blocker. Okay. 20 weeks, 4 months, that's it, done, no more. Okay. Did they stop working? Did the patient stop taking? How come there's this negative plateau with weight loss? How come lifestyle interventions stop working after a short period of time? How come? Very simple. It's called starvation. Okay? The negative plateau is because the brain, the body is smarter than the brain is. The body knows it's being deprived of nutrients. The body knows that there are fewer calories around to burn. And so what it does is it reduces energy expenditure to offset the change in caloric intake, to reach a new equilibrium. Okay, I'm going to show you that on the next slide. How does it do it? Well, it does it in 2 ways. First way it does it is it decreases something called non-exercise associated thermogenesis, also known as NEAT, also known as fidgeting. Have you ever noticed all these thin, wiry kids who fidget and flex arms? They're all thin, right? Okay. We give those kids Ritalin. Think about that. Okay? All they're doing is getting rid of the extra energy their body doesn't want to prevent obesity. That's all they're doing. Okay? So the sugar high, okay, that's actually real, because basically what it's doing is it's kicking up leptin, which is actually kicking up the sympathetic nervous system to actually expend the energy. Okay? It's a physiologically adaptive mechanism. It's normal, but we give rid of it. The other thing that happens is that our skeletal muscles actually cut back on the amount of energy they burn and the amount of heat they produce. Okay? And that's called mitochondrial adaptation. It's actually a change in something called uncoupling proteins. This physiologic adaptation is known as the starvation response. It's normal. It's what's kept us alive for billions of years in the face of famine, etc. Yeah.
Where does reverse T3 fit into those?
Okay. Basically, I'll show you T3. I mean, I don't know about reverse T3 because no studies with reverse T3 have been done in this phenomenon. But I'll show you T3 in a minute. Okay, that does fit. Okay, and this is a study done by Rudy Leibel, who is sort of my guru in obesity research. He was at Rockefeller when I was there, and he's now at Columbia. He's the head of the diabetes center there. And this was a study he did many years ago, where basically what he did was he took a bunch of fat people. Okay? He threw them in the clinical research center at Rockefeller University, okay, and he threw away the key, and he kept them there for 2 years. And he controlled what they ate for 2 years. And so before he started trying to get them to lose weight, he actually made them gain weight, 10% extra. And that's over here on this slide. And what you'll notice is that the 10% extra here in black, compared to the white ones, which are the baseline, they're still burning energy at the same rate. They're still on this identity line, which is 50 calories per kilo fat-free mass. We all burn energy at the rate of 50 calories per kilo fat-free mass. Okay? And if you gain weight, you still do. But then he caused them to lose weight, 10%, 20%. And you'll notice they came off the line. Now they're below the line. Now they're burning energy at the rate of 42 calories per kilo fat-free mass. Basal metabolism. 42. They've become 20% more energy efficient because they're starving. Because that's what starvation is. It's an attempt by the body to try to hold on to calories and not burn, because you might die. Everybody got that? Okay, that's starvation. Okay. So what happens to your autonomic nervous system, which is the part of your nervous system that's in charge of either burning or storing the energy? Well, in response to this decline in leptin level, which happens as you lose weight, okay, you get a reduction in the part of your nervous system that controls energy expenditure, called the sympathetic nervous system, and you get all of these things happening, which basically make you burn energy less fast. Okay? In addition, you increase another part of your autonomic nervous system called the vagus nerve. Anybody know what the vagus nerve is? The energy storage nerve. Everything the vagus nerve does is designed to get energy from the outside world into your fat. Okay? Everything. It's part of the hunger response. It's what makes your stomach make hydrochloric acid to digest the food. So it makes your intestines move around, called peristalsis, to absorb the food. It goes to your fat cell and makes the fat cell more sensitive to the hormone insulin, so that you can store more. It makes the pancreas make more insulin so that you can store more. Okay? Everything it does is designed to get energy from the outside world into your fat. And so it goes up in activity in an attempt to try to slow your heart rate so you won't burn as much energy and to get basically back to a normal leptin level. Okay? This is adaptive. This is supposed to happen. Okay? So the recidivism of obesity is not because people, fat people are gluttons and sloths. It's because they're starving. Okay? This is a complicated slide, and I'll let it go. But I think you have it in your handout. Okay? And it basically shows how the sympathetic and the vagal systems impact on both the adipocyte and also on the pancreas. We'll let it go for now. Okay? This is just a little too complicated. This is my favorite patient over here. Everybody know who that patient is? Okay? HIPAA forces me not to be able to divulge his identity. Let me just say that he is the OB mouse. This is a leptin-deficient mouse. This mouse can't make leptin. He has a gene mutation in his leptin gene. Therefore, his leptin is 0 all the time. Every minute of every day, his leptin is 0. So what does his brain see every minute of every day? He's starving. Okay? Does he look starving to you?
No.
Okay? But he is starving. That brain is starving. How much activity do you think this animal does? None. This animal sits in the corner of the cage and stays there. The only reason this animal ever gets off his hiney is if you put the food on the other side of the cage, he'll walk over and get it then, and then he'll sit down there. That's all he does. Okay? And nothing ever changes because this animal is chronically, constantly starving. So he'll eat anything you give him. All of it. And some. And nothing will ever fix it. Got it? Well, there are leptin-deficient people. Okay? This is the growth curve of a kid 10 years old at this point, who at birth was perfectly normal in terms of weight, and then started gaining weight right out of the box. Here's the 98th percentile over here. And you'll notice this kid's just taken off. This kid's 100 kilos, 220 pounds at age 10. Okay? Because he's constantly starving. But then, they gave him a shot of recombinant leptin every day, okay, that they made in the test tube. And look what happened. He lost weight on a dime. And what did he lose? He lost fat mass. He didn't lose lean mass. He didn't lose muscle. He lost fat. How come? Because now he wasn't starving. Right? Why would you lose muscle mass? Now he started to move. He started to exercise. His muscle built up, but he lost fat mass. Because now he wasn't starving. Everybody see what's going on here? Okay, good. And here he is, okay, at age 3.5. And here he is at age 8, having gotten a shot of leptin every day for those 4.5 years. Indistinguishable from normal. Okay? Drugs do work. If the drug is targeted to the problem. No, that's a drug. It's a hormone. It's a hormone replacement therapy is what it is. It's human leptin. That's right. Sure. It's not supplement. Well, we can argue about what it's supplement. It's bioidentical, and it is hormone replacement therapy. Okay, you call that something. Okay, fine. You call that something. Fine, you call that something. Okay? Because we're giving back what's missing. Okay? And it works. Okay? The problem, of course, is there are only 11 people in the world who are leptin deficient. And they're all Pakistani, and they all live in the UK, and they're all from consanguineous marriages. What about the rest of us? Well, the rest of us are not leptin deficient. In fact, we have plenty of leptin, as this slide shows. Here's percent body fat against leptin, and as you can see, it goes up as the body fat goes up. Because the rest of us are not leptin deficient. We are leptin resistant. We got plenty of leptin, but our brain, for whatever reason, can't see it. Because if our brain could see it, we would not be fat. Right? Because our sympathetic nervous system would be in overdrive. It would be causing us to exercise like crazy, and we wouldn't be hungry, and we'd go back to the way we should be. But we don't. Because our leptin ain't working. We are leptin resistant, not deficient, resistant. The question is, what is leptin resistance? And that's what the rest of part one is going to be about, is what is that? This just shows you, if you're leptin resistant, and you give fat people who are leptin resistant a shot of leptin every day, what do you think would happen? Nothing. Nothing. And that's what this group said showed. Nothing happened. You say, what about this group over here? Huh? No, they can't stay about the same. Stay about the same. What about this group over here? Well, they lost about 6 kilos over the course of the 24-week study. But the thing you need to know is that 18 patients started and 2 patients finished because of side effects. Okay? So, leptin doesn't work, and Amgen has basically divested itself of leptin after its $30 million investment, and Amylin Pharmaceuticals now has it, and they're trying to figure out what to do with it. Okay. This is probably the most important slide I'm going to show you the whole night. Okay, so everybody needs to understand it or we don't go on. All right? So this was also done by Rudy Leibel, along with his colleague Mike Rosenbaum, who was a fellow with me many years ago. Good guy. And what they did was very ingenious. They took a bunch of people, fat people, and they put them in their CRC again, and they locked up the, they locked the door, threw away the key, and basically got them to lose 10% of their body weight. And they studied them 3 times. 3 times. First time here in blue, the beginning, at baseline, before anything happened. Then they made them lose weight by calorically restricting them to get down to 10% reduction. And then they studied them a second time in this reduced weight or starvation state. And then they did something very smart. They gave back just enough leptin so that their leptin level was the same as when they started. Injections. Daily injections to get the leptin level back to where it was before they started the study. Okay, that's all. So physiologic replacement, not pharmacologic overdose. Got it?
They're still eating the same.
Still eating the same as the starvation diet. They're still on the starvation diet. Okay, got it? So what happened? Well, here's the leptin at baseline. Here's the leptin in the reduced weight state, and here's giving it back. Okay, everybody got it? So what happened? Well, body weight went down, and we went down a little more. Fat mass went down a little more. So did fat-free mass. Here's the important thing. Energy expenditure. So it went down, as you'd expect, because of this adaptation, the starvation response. And then they gave the leptin back. And now they're burning energy at the rate of 50 calories per kilo fat-free mass. Again, they were leptin resistant, but now they're not. Here's their thyroid hormone, their T3, who asked me. Okay? And you can see it went down, and then they gave the leptin and it went back up because they could burn energy now. They couldn't at baseline at the same dose, at the same level, but now they could. These patients had to have gone from being leptin resistant to being leptin sensitive. Something about weight loss caused them to switch from being leptin resistant to leptin sensitive. Does everybody understand that? Okay, because if you don't understand, you can't understand the rest of what I'm going to say. You have to understand this.
How do you know that in the middle there, they were leptin? So in that middle point, were they leptin resistant at that time?
Oh, I'm sure they were leptin sensitive, but they didn't have it.
Yeah.
Because now they were leptin deficient. So now they're getting it back, and now they can respond to
Why
it.
do they need an exogenous source of leptin to get them up to the right level?
Because their fat is now smaller, so their leptin's gone down, because that's where the leptin comes from. It's from the fat. Yeah. It's a marker of how big your fat cells are. So when your fat cells shrink, your leptin goes down.
So here I am with not very many fat cells, right? I have normal leptin level.
You have a normal leptin level for you, because it's genetically determined. Okay? If I had your leptin level, I'd be starving.
I thought my sister, when she was 25 and smoking, was normal weight.
Right?
And then now she's 300 pounds at age 60.
Yeah, her leptin level sucks now. It's really high. Okay? But it was probably normal back then. Yeah.
Did they collect any data on T4
T3.
so that
Just
they
T3.
have any way of knowing whether the T3 change was mediated by the thyroid gland
No.
or by some peripheral conversion?
No. No. That was slow. Okay. Everybody got that? Okay.
So how is leptin affecting the pancreas secretion of insulin?
That is a very complicated question, and the short answer is we don't know. Okay? It's a very complicated issue. There's some direct effects. There's some indirect effects through the hypothalamus. Bottom line, we don't know. It's a good question. I'm going to have to table it for now.
Would you repeat the main point? So the main point is that when you lose weight, you become leptin sensitive, right?
While they're losing weight.
While you're losing weight, your leptin all of a sudden starts improving its effectiveness. The problem is you've lost leptin because you've lost weight. That's the problem. Leptin's going down, but your sensitivity is going up. As your leptin goes down, your sensitivity goes up. So you can respond to exogenous leptin now. Yes?
I've had two friends who have lost weight unexplainably. And does that have anything to do with leptin?
Well, I can't answer exactly, without knowing their medical histories, et cetera. One of the big issues is cachexia, like from cancer. Okay? And cancer bypasses leptin. Because the way leptin works in the brain, it works at the ventromedial hypothalamus, but there are two way stations beyond, which I didn't get into just for time. Okay? The cytokines that are released from cancer cachexia actually work on those way stations and basically mimic the effect of leptin and make you not want to eat and make you burn energy faster so that you lose weight. The problem is then it's maladaptive instead of adaptive. I can't answer what's going on with your it could be a chronic disease state like Crohn's disease or something like that.
They were healthy.
Well, I
Just
don't
got
know.
skinny.
Well, they got lucky, I guess. All right, can we go on?
Yes.
Got a lot of slides. Okay. So I'm just going to, you've all heard what I've said already. I just want to make sure you understand that leptin resistance is the holy grail of obesity. If we could fix that, there wouldn't be obesity. Because then your own leptin would work, and it would keep you normal weight. So something about what's happened to our society from that first BMI slide I showed you is telling us that something's gone wrong with our leptin. Okay? This is about leptin resistance. This whole phenomenon of obesity is about leptin resistance. Yeah?
What in our food system or water system is affecting us?
Can I finish? Can I finish? Okay. Well, what causes leptin resistance? In fact, there are three ways to think about leptin resistance. There's the genetic models, there are anatomic models, and there are functional and environmental models. Okay? And we're going to go through each one briefly. Okay? This is a very complicated slide. This is a hypothalamic neuron. Okay? This is the neuron that responds to both leptin and insulin. Okay? And here's leptin, the leptin receptor over here, and here's the insulin receptor over here. The two of them bind to their respective receptors, and then they trigger off a cascade of events inside the cell that do stuff.
Membrane going across there.
That's a membrane going across there. Lipid bilayer. You bet. Okay? Let's just take the leptin side over here for a minute. Okay? So if leptin binds to its receptor, the first thing that happens is it activates an enzyme over here called JAK2, Janus kinase 2, which then causes the activation of this guy over here called STAT3, signal transduction transactivation 3. You won't be tested on this. Okay? But these two are the effector molecules of leptin. Okay? If you knock either one of these out in a transgenic knockout model, okay, that animal becomes leptin resistant because they can't transduce the leptin signal inside the cell. Okay? And of course they become massively obese, as you'd expect. That's old news. Here's what's interesting. Okay? Let's take those two away, and now we'll go to these next ones over here. IRS2, SH2B, and PTEC. These are in the insulin signaling pathway, not in the leptin signaling pathway. If you knock these out, you also get leptin resistance. If leptin signals its receptor, if insulin signals its receptor, how come if you screw up the insulin signal, you get a leptin resistance? It turns out it's a very complicated business, but in fact, insulin is the answer to leptin resistance, and I'm going to show you that. Okay? I'm going to show you clinically, I'm going to show you in patients. We'll go there. All right. Let's go now to anatomic models of leptin resistance. The ultimate leptin resistance. This is where I come into the story. This is my research now. Okay? This is a 15-year-old boy, my index patient, if you will. Okay? This was when I was at St. Jude Children's Research Hospital in Memphis, Tennessee. We took care of a lot of kids with brain tumors. And this 15-year-old boy in this slide weighs 364 pounds. Okay? When he was 7 years old, he was perfectly normal weight for height. Normal kid. And then he developed a hypothalamic chiasmatic astrocytoma, GUMBA, sitting right in the middle of that energy balance pathway. And he needed surgery, and he needed radiation in order to kill that tumor. And he became hypopituitary because his hypothalamus wasn't telling his pituitary what to do. And he needed all the hormone replacement therapies. And he started gaining weight at the rate of 30 pounds a year, nonstop, ad nauseum, ad infinitum. Normal kid before, now massively obese. And this was a good kid with a good mother who tried very hard to watch his diet and get him to exercise. And it didn't matter. 30 pounds a year, nonstop. That's all I saw. Okay? This
You sure his thyroid is properly?
absolutely, totally, properly taken care of. Perfect. And growth hormone replaced. Okay? Everything.
What do you mean by the term index patient?
Meaning the patient that got me started in obesity.
Oh,
Okay? My index patient.
yeah.
Okay.
Thank you.
Right? This form of intractable obesity that occurs because of damage to this pathway is called hypothalamic obesity. Okay? And the question is, what's wrong with these kids? This slide is hard to read, and I won't bore you with the details, but basically, this is energy intake up here. And it turns out that the energy intake of these kids is the same as normal obese kids. No different. But look at their energy expenditure. Way down. These kids don't move. They're hormone replaced up the wazoo. They don't move. They sit and they do nothing. These were kids who used to be active members of, their baseball team or whatever else. And they now do nothing. Nothing interests them. They sit like lumps of rock. And it's the thing that the parents complain about the most. I had a kid before. Now I have a blob of jello. Why? Because their brain thinks they're starving. Because they can't see their leptin, because those neurons are now dead. So this is organic or anatomic leptin resistance. Those neurons are dead. They can't see their leptin. They got plenty of it, but they can't see it because those neurons aren't alive to see it. So their brain always thinks they're starving. And so they eat like a normal obese kid, but they're gaining weight faster than any obese kid because they're not moving. Everybody got it? So this is a different form of leptin resistance, but nonetheless, very real. Okay? So the question is, how does this come about? And there are two hypotheses that have been promulgated over the years. The first one over here, that says damage to that hypothalamus does lead to obesity through a hyperphagia black box type of system. Anybody take Psych 101? Probably learned about this. You put two electrolytic lesions on the VMH on either side. The animal eats like there's no tomorrow. Okay? Everybody thought that was a satiety center you were knocking out. Okay? Garbage. There is no satiety center. Okay? This other hypothesis has been around actually for longer, which says that damage to the ventromedial nucleus, yes, it does lead to obesity, but through a more circuitous route. That damage to the VMN actually increases the vagus nerve. Because you're leptin resistant. Because you can't see your leptin, therefore your brain thinks you're starving, therefore, just like before when I told you about starvation, your vagus nerve goes into overdrive because it's trying to get more energy from the outside world into your fat. Everybody got it? And that increase in vagal firing rate goes to the pancreas, which makes insulin, and makes the pancreas make more insulin, and that excess insulin does what it's supposed to do, which is drive energy into fat. That's insulin's job. We take a diabetic off the street, blood sugar's 300. We give him a shot of insulin. Blood sugar goes down to 100. Right? Good, right? We did the right thing, right? Where did the 200 points go? Into fat. For storage. Because that's insulin's job. Insulin is the energy storage hormone. Insulin makes fat. More insulin, more fat. Got it? Very important you understand that. That is insulin's job. It's supposed to do that. So if you make too much insulin, you're going to make too much fat. These kids make too much insulin. We've actually shown this. Okay? So to understand this, we have to understand the endocrinology of the adipocyte. The adipocyte is not a piece of blob of jello sitting on your thighs looking bad. Okay? I mean, it is, but that's not all it is. Okay? It makes all of these hormones and cytokines here in blue, and it also responds to all of these hormones here in orange. Let's look at the ones it responds to. catecholamines, growth hormone, IGF-1, cortisol, sex hormones, those are all lipolytic. They all cause fat to be released from the fat cell. The only one that's consistently lipogenic, that is, put energy into fat every time, is insulin. No insulin, no fat. Too much insulin, too much fat. What does insulin do to the adipocyte? 4 things. Stimulates the glucose transporter to get the glucose into the cell. Stimulates these 3 enzymes, these 2 enzymes that are involved in fatty acid synthesis to deposit it in the cell, and it stimulates this enzyme over here, lipoprotein lipase, which snarfs lipid off circulating lipoproteins and throws it into the cell for storage. So every single thing that insulin does to the adipocyte is designed to make it take up energy. More insulin, more fat. Yeah.
So there's another whole mechanism here, that is, you have insulin resistance. You're going to be making more insulin, therefore driving more fat.
Right. Absolutely.
What does that tie in?
We're getting there.
You're going to tie them.
That's part 2. That's part 2. That's after the intermission. Okay? That's after the intermission. We'll get there. Okay? I promise we'll get there. I'm going to pass by this very quickly. This is just to show how the vagus nerve innervates the beta cell to make extra insulin. There's this KATP channel that has to close. This voltage-gated calcium channel opens. The vagus nerve basically interferes with 3 different mechanisms within that beta cell to cause extra insulin to be released. Okay? That's all you need to know. The vagus nerve is designed to up the insulin ante out of the beta cell. Okay? That's what you need to know out of these slides. Don't bother with the specifics.
Is that an excitotoxic mechanism?
No, it's not an excitotoxic mechanism. No. It doesn't hurt the beta cell. It just revs it up. Okay?
Okay, but the calcium channel is.
It's a voltage-gated calcium channel. It's not an excitotoxic. Okay. So the question I asked myself, okay, 11 years ago now, in 1996, was, what can I do for these patients? They're gaining weight on me like crazy. The parents are absolutely devastated. The kids are devastated. Their lives are complete and utter shambles. We saved them from their brain tumor, and they're going to die of their obesity. What the hell can I do for them? How can I stop this? Well, so my knowledge of the beta cell, I said, okay, this voltage-gated calcium channel is very important for this cell to work. Can we poison it? Can we stop it from working? Can we inhibit it from working? Turns out there is a somatostatin receptor that is coupled to that voltage-gated calcium channel, which revs it down. It brings it down. And we have a long-acting somatostatin analog at our disposal called octreotide, normally used to treat acromegaly. But we said it also suppresses insulin. So let's give octreotide to kids with hypothalamic obesity. And let's see if it works. Okay, so we did this first time in 1986. So our pilot study, done back then, was to look at the insulin secretory dynamics of these kids, to look at whether octreotide would knock it down, and to see whether octreotide would cause them to lose weight. 8 patients, open label trial. Everyone got drugged. Okay? Now the thing you have to know before we show you the data is that George Bray, the father of obesity research in America, in 1975, took 8 of these kids and locked them up on his clinical research center at UCLA Harbor Medical Center and fed them 500 calories a day for a month. Okay, starvation diet. 500 calories a day for a month. What do you think happened? They what? They gained weight. Thank you. They gained weight. On 500 calories a day, they gained weight. How can you gain weight on 500 calories a day? If you're starving, it's easy. That's right. Exactly. If you're starving, it's easy. These kids are starving. It doesn't matter how many calories they get, they will store it before they'll burn it. That's how sick this syndrome is. Okay? Got it? That in and of itself refutes the first law of thermodynamics as you interpret it. Okay? Yeah.
The problem is, if you carried that experiment out 6 months, they would not lose weight.
Yes, they would.
If you carried
Well,
that-
1 month. I mean, who would do it for 6 months?
Nobody is stabbed in Auschwitz.
Right.
Did not exist.
Right.
It's a time-dependent phenomenon. That was a short-term phenomenon.
Nobody was obese in Auschwitz because they were starving. Right. But these are kids with brain lesions.
Because you only did this for a month.
Well, George Bray did it for a month. I'm going to do it for 6. Okay? Because here's the 6 months. Okay? 3 kids lost a lot of weight. 4.3 BMI points. 12.6 kilos mean over 6 months. These are kids who gained weight on 500 calories a day. Now they're losing weight because I gave them a drug that suppressed insulin. 2 patients, moderate amounts, and 3 patients stabilized. At least they didn't gain more. But something even more remarkable happened because 4 of these kids started exercising spontaneously, out of the blue. Okay? 1 kid started competitive swimming. 2 kids started lifting weights at home. 1 kid became the manager of his high school basketball team. These are kids who sat on the couch, ate Doritos, and slept. And now they're exercising. They feel better. This is very interesting. So I said, okay, let's do a double-blind placebo-controlled trial. Okay? So we did that, and here's the data on that. So here are now, oh, sorry, I take it back. This is still the same pilot study. Here's what the insulins did. Okay? 300, 400, 500 microunits per mil. Normal's 100. These kids are releasing 5 times the amount of insulin, okay, as normal. 3 months of drug, starting to knock it down. By 6 months, we have a peak response of 114, totally normal. So we've gotten the insulin down to normal by giving this drug in this group. And the change in weight correlated with how well we got the insulin down over here. So, in other words, if we got the insulin down, these patients lost weight, and they felt better. So that led us to the double-blind placebo-controlled trial. 20 subjects with this disorder from around the country, 13 with a brain tumor called craniopharyngioma, which is the famous one for causing this. Okay. And here's the data on drug versus placebo. Placebo, continued weight and BMI gain, as you'd expect. Drug treated, we were able to stabilize them in this study. They didn't lose weight. The reason, because they were being followed at their home for the 6 months, and we only raised the dose at the 2-month and the 4-month level. Okay, and so they actually didn't go up to maximum dose till the 5th month, and that was when they started losing the weight. So in the first 4 months, they started gaining. They gained a little bit, and then they knocked down. So they were able to stabilize for the whole 6 months. Okay, but they felt better also. And here's what the insulins did at baseline, and here's at 6 months. We got rid of that whole early phase of the insulin response. Placebo, we did nothing. Because of the beneficial effects on these kids' quality of life, because they were starting to exercise, they felt better, we built a quality of life questionnaire into this study called the PCQL32, Pediatric Cancer Quality of Life. 32 questions, which ask questions about cognitive, physical, psychological, and social functioning. It's a proctored exam given by the same proctor each time. The parent is in one room, the kid's in the other. Okay, so there's no chance for cheating off papers or anything. And here's the data. They both fill out separate ones, okay, but in different rooms by the same proctor. Okay, so we know we're validated. Okay? And here's the placebo group. Nothing happened, as you expect. And here's the drug-treated group. The kids noticed improvements, although not statistically significant improvements, in psychological and social well-being. And the parents noted statistically significant improvements in physical, psychological, and social well-being. And when we did the intergroup comparison, the thing that fell out, these kids were more physically active on drug than they were off. Okay? These kids were now moving. How come they're moving? And it turned out that when we looked at the change in quality of life over here on the y-axis, it correlated with how well we suppressed the insulin here on the x-axis. In other words, if we got the insulin down, these patients felt better. Got it? Neat. And as far as I know, this is still the first and only direct, I shouldn't say proof, that's not quite the right word, but direct demonstration of a biochemical basis for gluttony and sloth.
So restricting sugar and starches has a similar effect.
We're getting there. That's part 2. We're going there. Yeah. Yes?
Yeah, okay, so just excuse me if I'm like jumping ahead or whatever, or jumping in the wrong thing. What about something like chlorglycine or diazoxide?
We tried diazoxide. The problem is it has a very small therapeutic window. We were in between studies, and we had one kid with a germinoma who came in and had gained an enormous amount of weight. And so we said, we don't have octreotide to give you, but we're going to try this other drug that also suppresses beta cell function called diazoxide. Here's a glucometer. I want you to do your blood sugars twice a day, and I want you to come back in a week. Okay? Kid did not come back in a week. Kid didn't call. Kid came back in 3 weeks, except he came back to the emergency room. The emergency room ER doc called me up and said, Dr. Lustig, I have your patient blah, blah, blah down here, and his blood sugar is 821. I said, I'm not doing this again. Okay? So diazoxide, the window is very small. Okay? But Ramin Alamzadeh actually treated premenopausal women with low-dose diazoxide along with a very low-calorie diet, and was able to show in a double-blind placebo-controlled trial that those patients on drug did better than the patients who were on the very low-calorie diet alone because their insulin went down. So maybe, but it's a very tough drug to deal with, especially in kids. Yeah.
If the vagus nerve becomes impinged for one reason or another, will you become insulin resistant perhaps?
Well, that's a good question, but if the vagus nerve becomes impinged, then you would basically lose your vagal tone, right? You wouldn't increase it, you'd probably lose it. And that's a very complicated question. We are actually doing laparoscopic truncal at UCSF right now as a clinical research trial. I can't report the results because we're in the process, but we're doing that right now.
What is these?
Sorry? Sorry?
What are these? You can't tell us.
Can't tell you. Okay? When I know the results, I can tell you. Okay? Because you don't want me to give you wrong data, right? You're naysayers. You only want proof, right? Right. It's not my nature. Okay? So here's a patient. Okay? 220 pounds over here, pineal germinoma. Here she is at 172 1 year later. And there's an apocryphal story about her. She was only on the drug for a week, and the mother calls me up and says, Dr. Lustig, I don't know what the hell's going on, but something's very different because we would go to Taco Bell, and she would eat 5 tacos and an enchilada, and now she eats 2 tacos and she's full. Hi, I'm in the middle of something. She knows where I am. I don't know what the hell she's doing. So here she is. Okay, and she's felt better. This was before she lost weight. Okay? It was only a week. Only a week. Okay? Here's another patient. Okay, this was the competitive swimmer. So here she is at age 10. BMI is 28. Here she is 6 months after on drug, and her BMI has gone down to 24. Okay, and she started competitive swimming. And here we had to stop the study because the study was over. We didn't have drug to give her. The insurance company wasn't paid for it because it was experimental. Right? So here she is 2¼ years later, desperately trying to do something about her weight, but it's swelled up to 34 and a half. We finally got her drug, and she settled out at a BMI of 27. Okay? Koch's postulates. Anybody know what Koch's postulates are? Prove something in medicine. Okay, you expose somebody to something, or an animal to something bad happens, you take it away, it goes away, you do it again, it happens again. Okay? Same thing. Koch's postulates fulfilled. And here's my proband index patient, 364 pounds over here, now he's down to 326. First time he took a picture with his shirt off. Okay. So what's going on here? Well, I would pose to you that this actually sort of defines what it's really about in general, but we'll just talk about this disorder right now. Each of us is really 2 compartments. There's you, your heart, your liver, your lungs, your kidneys, your brain, your muscles, your lean body mass, which burn it. And then there's your fat. Okay. 2 compartments. Now, the substrate for both compartments is glucose, but never at substrate saturation for both compartments at the same time. That's just too much glucose. There's never that much. Okay? Which means that there's a competition going on between compartments. Which compartment is glucose? What determines it? Well, your insulin does. The more goes to your fat. Okay? Now, your fat though makes leptin. And then your leptin goes to your VMH, and your VMH senses that, hey, I'm going to turn on my sympathetic nervous system, I'm going to increase my exercise, and that's going to reduce the amount of glucose going to fat and more going to you. And so you stay in yin-yang energy balance. Unless, of course, you can't see your leptin. Okay, this is basically dead, which is driving because you're in starvation mode, and that's driving your insulin, driving it confused. It's like a hormone. So that's that.
But the assumption on that slide is
Yes.
that there should be a lot of, that there's a lot of bunch of glucose. It's not at all clear that you need a lot of glucose.
That's true. But the fact is, it's got to go somewhere.
If you put it in your
Either you burn it or you store it.
If you put it in your mouth.
Right, but the point is that the vagus nerve's making you put it in your mouth.
When you put something in your mouth, your brain is deciding what's going to be, whether it's going to be Cokes or whether it's going to be.
Well, we're going to get there too.
Nuts.
That's part two. That's also part two.
After the break, David, yeah.
So let me move on, or we will never get to part two. So you say to me, okay, doctor, this is really a great parlor trick, but what the hell does this have to do with obesity? Propose to you everything, and here's why. This is a study done by Ron Siegel when he was at Joslin, and he had the natural history of weight gain in a normal population. So 7 normal adults, active audience, parents of type 2 diabetics being treated at Joslin. They weren't going. Okay? And he studied their weight gain over 15 years. And he did IV glucose tolerance tests and used glycemic clamps at the beginning and at the end. And he asked the question, what demographic, racial, and biochemical factors predicted the weight gain over a 15-year period? And so when he did the linear regression, multivariate linear regression model, the thing that came out that was the most demonstrative, the most predictive, was the acute insulin secretion. That early insulin secretion, the part that the octreotide knocked out, that was the thing that predicted the weight gain the best. He also had secretion data on everything, and he had resistance data on everything. And so he bisected all those groups of data at the median, 4 quadrants of 28 patients in each quadrant. So he had the low secretors who were resistant, he had the low secretors who were sensitive, he had the high secretors who were resistant, and he had the high secretors who were sensitive. Got it? And he asked, okay, of those 4 quadrants of groups, 28 patients, which group gained the weight? The high secretors who were sensitive. So that phase of insulin secretion in response to glucose, that's the weight gain phase. Insulin response curve. That's how high your insulin goes is how much weight you gain.
All right, please.
We did the kids. Would they lose weight and would they feel better? That's what we wanted to know. Okay? We didn't know what these patients looked like. Okay? So we did an all-comers pilot study, 44 patients, 24 weeks, and here's what we saw. 8, here in green, 8 patients lost 12.6 kilos in 24 weeks. 4.3 BMI points in 24 weeks. Pretty amazing, if you ask me. Okay? 8. The other 36? No. So who were these 8 patients? Who were they? Why did they lose weight when the others didn't? Okay? Interestingly, we looked at their dietary. They were keeping dietary. And it turned out that the protein and the fat intake was in all the groups. Okay? Over the course of the trial. But look at the down on it. They went from 900 calories a day ingested to 350 calories a day ingested. They cut their carbohydrate intake by 65% voluntarily, spontaneously, with no prodding from you. But only the group. Okay? And so their total percent calories from carbohydrate went from 47 to 35%. This is a change in food preference.
Spontaneously, that's all I'm going to do what I think I've heard will make me lose weight and watch what happens.
No, what I'm saying is that this drug made them not want to crave carbohydrate. Yeah, all of them were on the drug. No,
Because they
all
weren't
44.
starving?
Huh?
Sorry.
Sorry?
Voluntarily were cutting their carbs because they weren't starving?
Right. Exactly, because they weren't starving. Correct. Okay. So here's what their insulins look like at baseline. Straight up, straight down, like an inverted V. Quick release, fast clearance, an insulin hypersecretion with no insulin resistance. The orange guys over here. Slower rise, plateau, then down. That's the group that's going to get type 2 diabetes later.
Isn't it a lot what we hear about is just insulin resistance? I mean,
That's insulin resistance.
I've heard this issue of acute insulin
Well,
production.
you're hearing it now. Okay. All right, got it? Completely different insulin in the responders. So here's what their insulins did over the course of the study. Here's that same inverted V I just showed you, and here's on drug. We got rid of that whole first phase, just like the kids. Remember? Here's the non-responders. We didn't do anything. Why? Because the drug wasn't treating their problem. Whereas over here, the drug was their problem. Okay. Now, here's the most important thing I'm going to tell you about my work. They lost 12.6 kilos. They lost 4.3 BMI points. Their leptin levels went from 62 to 32. By 30 points, it went down by 50% in the responders. And the change in leptin correlated with the change in BMI, as you expect. That's not surprising. So here's my... What did their energy expenditure do? How could it go up? They lost 50% of their leptin. They're now leptin deficient.
What did he say?
We didn't hear you. They have to be less resistant.
They're now sensitive. Let me show you. Because here, look at this. This is interesting. At pre-study, they actually burn less energy. They're actually burning less energy to start with. And when we treated them, this is the group that lost the 12.6 kilos. Their energy expenditure stayed the same. In fact, per kilo fat-free mass, it went up. How do you explain a leptin that goes up and an energy expenditure that goes up? They must be leptin sensitive. We took them from a state of leptin resistance at baseline, and now they're leptin sensitive. What did Rosenbaum and Leibel do? They forced caloric restriction. And they took patients from leptin resistant to leptin sensitive. What did we do? We suppressed insulin. We took patients from leptin resistant to leptin sensitive. What's the similarity? The drop in insulin. The drop in insulin. And remember what I showed you, genetic knockout mice? Remember? In the insulin pathway, you knock it out, you get leptin resistance. There's something about insulin signaling that interferes with leptin signaling. Okay? Now, here's the cynic, the pièce de résistance of this whole business. Remember the 4 months, the negative plateau with all the drugs? Right? No more? If they're leptin, could they lose more weight? And indeed, we took it out for a whole year, and indeed, they did. Okay? They didn't stop because they're leptin sensitive. This led to a randomized double-blind placebo-controlled trial. And you'll notice that at each dose, the group that did the best was the group that had the highest insulin secretion, which is the same. In other words, the group that secreted the most insulin was the most responsive. Lost the most weight. They were the ones who also felt the most better. Okay. Come on. There we go. Here's a patient. Christmas 1998. She's holding up for Christmas bread, I think. And here she is 35 pounds later in her jogging togs. Showing off. Because she felt this is the whole idea. Leptin sensitivity was improved, right? How can we measure leptin sensitivity in humans? In animals, you give a shot of leptin, you see what happens. But I don't have leptin to give. Okay? So how do I do it in humans? Well, I need a surrogate measure for leptin sensitivity. So I said to myself, okay, let's get okay? Nice thin guy, right? He has a normal energy expenditure, low level of leptin. I have a normal energy expenditure at a high level of leptin. his REE to leptin ratio would be high. My REE to leptin ratio would be low, right? Because my denominator is higher. Now, resting energy expenditure. Okay? Let's say I tried to diet, and I brought my leptin level down. Right? What would happen to my energy expenditure? It would go down. No, it would also go down because that's starvation. So I said, oh, so that's a good, maybe that would actually work. It's a surrogate measure of leptin sensitivity within individual patients. I don't know if it works cross-sectionally, but at least within individual patients. So we said, okay, we had all of these pieces of information, and so REE to leptin ratio in the responders, because after all, REE went up when their leptin went down. So of course the ratio got better, right? So who cares? Well, here's why it's important. Because the change in the ratio correlated with how well we suppressed the insulin. In other words, if we got the insulin down, their leptin sensitivity improved. Correlated. In other words, the insulin was the cause of the leptin resistance. Insulin caused it. Okay. So, yeah, they're coupled. So I'm proposing to you today that insulin is actually an endogenous leptin antagonist. Okay? That's what it is. And it's there on purpose. The question is, why would God do this? Okay? Whenever this kind of thing happens in medicine or science, there's always a biological advantage. What the hell is the biological advantage of this system? The answer? Absolutely. And he does not play dice. Right. He's not playing dice here either. Okay? Why would this happen? What is the biological advantage? And the answer is very simple. What?
On conditions of privation and suffering, and starvation, this permits you to survive.
Absolutely.
Yeah.
And it also permits the survival of the species in times of plenty because of two processes which you care about, called puberty and pregnancy. Both of which states where you have to gain weight in order to accomplish them. If you're always leptin sensitive, how can you gain the weight? There has to be a period of time where your leptin doesn't work so hot in order to gain the weight, in order to be able to carry the baby to term. And once the baby's out, things go back in the other direction. Well, both puberty and pregnancy are inherently insulin-resistant states. The insulin goes up on purpose.
But you need to gain fat.
Sure you do. Oh, yes, you do. You bet you do.
A lot. How much fat? What do you need?
Well, to carry pregnancy, about 15. What about puberty? You need to carry fat. That's part of what reproduction in females is about. That's right.
So in other words, whatever your fat percentage is, if you're growing, you're going to need a little bit more fat.
Absolutely.
But keep the same percentage.
Without question. And if you don't have the fat, okay, you get metabolic syndrome. That's what the leptin deficient patients have taught us, and the AIDS patients have taught us. You have to have fat. You have to have fat. That's good for you. Sub-Q fat. Okay? So puberty and pregnancy are actually the reason why this exists. And so insulin goes up, which happens during both those states. It's normal to gain weight. And then when the two states are over, things go back to normal, and then you can either lose it or at least maintain it. Point is, that's when things are adaptive. But clearly something has happened in our environment which has made this now maladaptive. Okay? And so here's how I put the whole thing together. Okay, this is the end of part one. You asked the question. Okay? So here's obesity over here. Here's hyperleptinemia over here. The leptin should turn all of this stuff up here off. This is in your handout, so I won't belabor it. But clearly, the leptin's not doing its job because of leptin resistance, and we've hyperinsulinemia. Hyperinsulinemia is actually interfering with leptin production and allowing these things to basically go up, which of course is driving more obesity, more hyperinsulinemia, because after all, it shunts. It makes sense that the thing that makes the fat go in to the fat cell is the thing that would block the brain. Otherwise, you'd always be in chronic, normal, negative feedback. You could never gain weight. It's part of normal physiology, but it's maladaptive because now we have this. 2-minute stretch your feet break, and then we'll go to part 2. Okay? Remember the first law? If you eat it, you better burn it or you're going to store it. Bullshit. Okay? Here's the real way. If you're going to store it, look at weight gain set up by the high insulin, and you expect to burn it, that is a normal quality of life based on normal energy expenditure, then you're going to have to eat it. And now, all of a sudden, these two behaviors are subservient to a biochemical process rather than the other way around. From the outside, it looks like gluttony and sloth, but in fact, it's biochemical. In fact, all behavior is biochemical. Drinking behavior is biochemical. Sleep behavior is biochemical. Sexual behavior is biochemical. Why shouldn't eating behavior be biochemical? We have physicians in the room, right? You see a kid 10 gallons of water a day, urinating 10 gallons of water a day. What's the kid? Diabetes, right? Okay. You look at a behavior and you know there's a biochemical reason. You see a 25-year-old who falls asleep in his soup. What's he got? Which we now know is a defect in orexin signal. Okay? Schizophrenia. We now know is a neurotransmission defect. Come on. Get with it. Behavior is biochemistry. It always is. It always will be. That's what God did to us. Okay? I'm going to stop now at part 1. And then we're going to pick up in 2 minutes with why we now have all this insulin around. For kids, because that's treating insulin resistance. Well, it's not the death one. Not at all. Thiazolidine first of all, PPR gamma is an adipose tissue. Cause weight gain. If you're trying to lose weight, that's not the answer. It improves insulin sensitivity, which is good, but it also causes weight gain. So that's metformin we use a lot of, and I can show you metformin data. It's not in this talk. If you want, you can invite me back. I give a whole talk on pharmacotherapy for obesity, and metformin is front and center. Okay? Especially
at that point, you came to the conclusion that it's not created by
would work in this patient group. No, in this patient group only.
specifically in this patient.
Only in the high insulin secretors. Only. It doesn't work in others.
When you define high insulin, is this easily
An OGTT.
fasting?
OGTT. Have to do an OGTT. Have to because it's a stimulated insulin. Right. Right. You can't do it off of fasting. You can't learn anything. So insulin promotes obesity through 3 mechanisms. Okay? 1, driving energy into adipose tissue. 2, interfering with leptin signaling, that's the starvation response. And finally, interfering with dopamine clearance from the nucleus accumbens. But I didn't have time to show it to you, just trust me, or we'll be here even longer. So where does excess insulin come from? Well, it came from 3 places. 1, genetics. There are genetic predispositions to high insulin. It's called the VNTR, the variable internal insulin gene, has been shown to cause insulin hypersecretion. That's one. The French showed that. Epigenetics. That is, before you're born, what happened to you. Okay? Small and large for gestational age babies both end up obese with metabolic syndrome as adults. The question is, what's wrong with those 2 states? What do they share in common? A starvation state. One's an over-replenishing state. The thing they share, they're both insulin-resistant states. Insulin resistance is actually changing your brain while you're developing. And finally, there's the built environment, like labor-saving devices and urban planning. I don't know about the rest of you. When I was a kid, I went around and mowed every lawn on my block with a manual lawnmower for a quarter. Okay, the last time you saw that. Okay? But you never see that. Anybody do that anymore? Okay? The stress environment, cortisol. If you don't think our kids today are stressed, okay, it's a huge problem. Okay? And cortisol is driving visceral fat deposition and insulin resistance. And finally, the food environment, which is what we're going to talk about now. Okay? Specifically, fiber and fructose. Too much, not enough. Okay? That's where we are. Okay? So here's the evolution of fast food. Everybody remember, this is the original White Castle ham. 1 ounce, 218 calories. Bob's Big Boy, okay, at 618 calories. And in the midst of this obesity epidemic, Hardee's had the temerity, the absolute audacity to introduce the burger at 1,420 calories. So you'd say, well, you know, that's the reason for obesity. Well, yes and no. I mean, I just called it yes. Insulin is the reason for the obesity. But when insulin's high, this is what happens. So let's look at where the caloric intake in kids is. In fact, kids are drinking taking in 275 calories more per day. And I want to thank my colleague, Dr. Andrea Garber, for these slides, who's here today, encouraging me on. She's our dietitian nutritionist at UCSF. 275 calories in teens. Okay? Where are they? They're not in fat. It's only a 5-gram increase over that time. That's nothing. Where is it? Here's where it is. 57 grams, 228 calories in carbohydrate. And specifically, well, we'll get there. Calories from fat have gone down. Obesity prevalence has gone up. Okay? Snack wells. Remember snack wells? Okay? Low fat, right? Didn't help. Okay. So, why? Well, one reason is something called glycemic load. Everybody heard of glycemic index. I'm sure that's a big word. But glycemic load is the thing that matters because that's glycemic index times the amount of carbohydrate you have to eat, and that volume you have to eat to get the 50 grams of carbohydrate. Like, for instance, carrots. Carrots have a high glycemic index. If you eat 50 grams of carbohydrate in carrots, your blood sugar goes up higher, which means your insulin goes higher. Okay? But you don't need a whole room-weight truck to get 50 grams of carbohydrate in carrots. So therefore, glycemic load in carrots is low. So we like carrots. Carrots are good. Okay, as an example. Okay? So beans, lentils, other nuts, other legumes, almonds are really good. They have lots of fiber. So what is fiber? Also the biochemical composition. Here's amylose, which is alpha-1,4 linkage. This is what's in beans and lentils and other legumes. That's why you get gas. That's why you get flatulence. Okay? Because the bacteria are fermenting also. And over here you have amylopectin. It has the alpha-1,4 and the alpha-1,6 linkages, which allows for the branching. Problem is, this gets converted to glucose super fast because you can have an enzyme over here, you can have an enzyme over here, you get the branching here, and you can basically take something that's huge in a very short period of time. And so that's going to raise your blood sugar super fast. Okay? So amylose, only 2 enzymes at one time, working from the outside in. And so you're going to release blood sugar a lot slower. And that means your insulin response is going to be a lot lower. So that's where glycemic index and load come from, is the starch thing. But also the fiber, because when you go out into the field and you harvest the wheat, what color is it? It's brown, right? Why? Because it's bran, right? The thing that's surrounding the starch molecule. The endosperm is on the inside, but the bran is the good part. That's the part you want, the fiber. And you all know this because that's what okay, but the people out there don't know. And in fact, if you look at this IRAS study, the insulin-resistant atherosclerosis, they actually looked at all the components of food and saw what correlated with the insulin sensitivity. The only thing that correlated was the dietary fiber. The fiber is the good part. The fiber is the good part. Okay? We tell kids, don't drink fruit juice. Okay? Why? Because fruit has fiber and juice doesn't. Okay? The juice is the bad part of the fruit. The fiber is the good part of the fruit. The juice is nature's way of getting you to eat your fiber. Okay? That's one of our messages that we do. Okay? Sorry? Yeah. Okay. Beneficial effects of fiber in preventing obesity, 3 things. Number 1, it moves the food through the intestine faster, so you get that PYY signal sooner, and therefore you won't have that portion. So that's why it's considered okay? Number 2, it reduces the rate of absorption from the gut into the intestine, keeping the insulin response down, which I just showed you is important. And finally, something else that's kind of interesting, it allows more carbohydrate to reach the colon, where it gets fermented by bacteria in the colon to short-chain fatty acids, which suppress beta cell insulin release. Whereas long-chain fatty acids, real culprit in this whole talk is beverage intake. That's where the real dollars are. 41% increase in soft drinks. Okay? Just remember, a can of soda a day is 150 calories times 365 days a year divided by the magic number of 3,500 calories in a pound. So that's worth 15.5 pounds a year. We actually do this in clinic. We pull out the calculator and we say, okay, how many cans of soda, how many glasses of orange juice? Okay? And we actually do the math for them, and basically, it almost always explains the kids' weight gain. Almost always. So, are soft drinks the cause of obesity? Depends on who you ask. If you ask Richard Adamson, the scientist of soft drink association, there is no association between sugar consumption and obesity. However, my colleague, Dr. David Ludwig at Boston Children's, I'm Lustig, he's Ludwig, we do the same thing, he's a really good guy. He showed drink increases your odds risk ratio by 60%. Odds risk. Your risk compared to the general population. Each sugar drink increases your risk by 60%. Here's a study that was done in JAMA 2004, looking at total amount of drink consumption. And you can see the greater than one drink a day were the ones who gained the most weight. Not surprising. This is our soft drink type 2 diabetes. So here's less than once a month, less than once a week, more than once a week, more than once a day. And just look at the odds risk ratio going up. Doesn't matter if it's soft drinks, cola, fruit, they all go up. And they're clearly statistically significant. Okay? And Koch's postulate. Fizzy drink study from Christchurch, England, published in 2004, where they took the sodas out of the schools. Sound familiar? Okay. And notice that the prevalence of obesity in that population basically stabilized, whereas the control group just kept going up. Okay? Just by taking it out. Okay? So, what's happened to our society over the past 30 years? Michael Palo will tell you, we've been cornified, right? Cornified. Okay. Here's the advent of corn syrup on prices. So here's the producer price index. Everybody know what that is? Not the consumer price index, the producer price index. It's a method for figuring out the stability of prices over time. And you'll notice that high fructose corn syrup came in 1980, and you can see what was going on before. And since high fructose corn syrup right here in yellow, basically things stay relatively constant. Here's the international price of sugar stabilizing out. Here's the American price of sugar having gone down. Okay, this is the sugar. So it's stabilized the price of sugar. Okay. And here's the US price of refined sugar, gone way down. And here's high fructose corn syrup, even cheaper. Okay? High fructose corn syrup is bad, not because it's high fructose corn syrup. It's bad because it's everywhere. It's in fact the same as sucrose, and I'll show you that. Okay? This is consumption data, okay, from the U.S. Department of Agriculture. So here's high fructose corn syrup. Here's sugar. The Corn Refiners Association says, well, all we did was substitute. Wrong. Okay, because here it's 73 and here it's 95. Okay? We're eating okay? And I don't know if you can see this one, but this is basically pounds per year of sugar per person. And it reached a peak at 90 and it's just stayed there. 56 pounds per year. Okay? We didn't do that.
Though that when you go from cane sugar to corn syrup, you double the
No, I'm going to show you. No, that's not true. This is just the relative sweetness of various carbohydrates. So here's sucrose at 100. That's sort of your index right here. High fructose corn syrup's here at 120. A little sweeter, right? Straight fructose is 173, but there's nothing in nature that's straight fructose. In fact, there's nothing that we even in man-made that's straight fructose, except in but I mean, nothing you can buy, in a food. Okay. Like, that's right. You can't really do that. Okay? But the point is that stuff is sweeter, but they use just as much. And so it's actually changed our taste buds as we've gone. Okay? And depends on who you talk to. The Corn Refiners Association are very, very adamant that high fructose corn syrup metabolizes and impacts satiety very similar to sugar, exactly the same as sugar, in fact. And I just wanted to point out that this was all done by the American Beverage Council and the Corn Refiners Association. Presented at academic meetings. Okay? And in fact, I actually agree with them. In fact, high fructose corn syrup and sucrose are no different. They're exactly the same. Because high fructose corn syrup is 42 or 55% fructose. Sucrose is 50% fructose. Here's sucrose right here. Here's the glucose. Here's the fructose.
This fructose half sucrose and half glucose?
No. Well, sucrose is half glucose, half fructose. Yes. Sucrose.
Right.
Right. And high fructose corn syrup is basically half glucose, half fructose. Okay. The only thing with high fructose corn syrup is cheaper. Because they took the corn syrup and they put it in something called glucose oxidase, which actually stereoisomerizes the glucose to form fructose to get the fructose content up. Okay? Top Saga Medical School, 1966.
Would it be worse for us?
Well, depends. Cheaper? No. Better? Okay. This is just to show you that it doesn't matter if it's high fructose corn syrup or not. This is fruit juice. Okay? Plain old fruit juice, orange juice. Okay? Nothing added. Tropicana. Okay? Orange juice. Okay? Showing that in lower socioeconomic kids in Harlem, okay, ages 2 to 5, the number of juice servings per day correlates with the degree of weight gain per month. Okay? Remember, the problem here is that fructose is not glucose. Fructose is very dangerous. Fructose is a poison. Same thing. It's not all glucose. No, it's not all glucose. It's the same thing. It's all the same. Okay? Fructose does a lot of things that glucose does not. Fructose is 7 times more likely to form advanced glycosylation end products, which I'm sure you all know about, the amyloid rearrangement, hemoglobin A1C, right, and diabetes, right, causing vascular problems, right, basement membrane problems. 7 times more likely based on the exothermic reaction, the Maillard reaction compared to the amyloid reaction. Okay? What the corn refiners say is, yeah, but you never get up that high. The fructose level in your blood is so much lower. Not. So every bolus, you're basically your arteries, and that's actually been shown in basic science. Fructose does not suppress the hunger hormone ghrelin. Ludwig did a very nice study where he gave everybody a can of soda and then saw how much they ate at the restaurant afterwards. And guess what? They ate just as much whether they had the can of soda or not first. Okay? Because it didn't suppress ghrelin. Whereas the does not stimulate insulin because there's no receptor for fructose on the beta cell. Okay? So Peter Havel, my opposite number at UC Davis, like to argue about this point. He thinks that that's the reason why fructose causes obesity, is because it doesn't stimulate insulin, therefore the leptin doesn't go up. And if the leptin doesn't go up, that's why you're obese, is because it didn't go up, so therefore your brain didn't get the signal. Okay? That's acute. But the problem is it causes such severe insulin resistance, the insulin's up all the time when it's chronic. And no one drinks one fructose. Nobody can drink just one. Okay? Hepatic fructose metabolism is different. I'm going to show you that in great detail. And chronic fructose exposure, I'm going to show you, can promote the metabolic syndrome all by itself, with nothing else. I'm going to show you some data from our clinic. This is the Watch Clinic. These are our baseline characteristics. Here's our breakdown in race ethnicity. Here's how fat our kids are. Median of 33.2 BMI with a 2.5 BMI Z-score. That's pretty darn fat. And here's their fasting insulin of 21 and their HOMA, which is 4.3, which is pretty bad. Okay? That's where we're starting. Now let's talk about glucose first.
You should explain the
HOMA is the homeostatic model of insulin resistance. It basically tells us how insulin resistant someone is. A good HOMA would be something like 2. Okay? A bad HOMA would be like 7. Our patients are like 4.3. Okay? Everybody got the picture? So let's talk about how glucose gets metabolized. And I'll show you that fructose is a real problem. Okay? So So here's glucose out here. There's some here, there's some here. Okay? Turns out that only 20% of the glucose you ingest ends up in the liver. Most of it ends up in other organs, because other organs can use glucose directly. So if you drank 120 calories of glucose, or ate 120 calories of glucose, like let's say you ate 2 pieces of white bread, okay? Only 24 of those 120 calories would make it to the liver. The rest of it would be metabolized by other organs. Okay? So that's a relatively small bolus of glucose. Got it? So the liver's not handling much. So first thing that happens, glucose comes in through this transporter called GLUT2. Okay? And the glucose is stimulating insulin over here, binds to the insulin receptor, activates the IRS1, which activates this enzyme here called AKT, which is going to basically do the busy work of insulin inside the hepatocyte. It then AKT stimulates this guy over here, SREBP1. Don't worry about what these things are. That's not important. Okay? I'm not showing you this because I want to really demonstrate the biochemistry to you. I just want you to see how fructose is different. Okay? Just leave it at the fact that this exists, and there's animal data for every one of these points. Okay? SREBP1 stimulates this enzyme called glucokinase to get it to be glucose 6-phosphate. That's the way you trap it inside the hepatocyte, because then, from there, you stimulate glycogen synthase, which then forms glycogen. Glycogen is the storage form of glucose in the liver. How much glycogen can you store before your liver gets damaged? An infinite amount. Because we have kids with glycogen storage diseases. Their liver is down to their knees, and their liver works fine. Okay? Glycogen is non-toxic. Glycogen is a perfectly acceptable storage form of glucose. Okay? Of energy in the liver. Okay? It doesn't matter how much you make. Now, some of it's going to leak out and go down this pathway called the Enden-Meyerhof pathway, or the glycolytic pathway for those of you who took biochemistry, to come to something called pyruvate. That enters the mitochondrion, which is this guy over here, which then enters the tricarboxylic acid, or the Krebs cycle, for those of you who know about these things. And that generates ATP and carbon dioxide, which is the whole point of energy metabolism in the first place, is to make that stuff. Now, a little bit, that which does not get metabolized through this, a little of that citrate over there is going to exit, called the citrate shuttle. And so it's a very small amount. And that SREBP1 is going to stimulate these 3 enzymes here that are involved in fatty acid synthesis. Okay? And so that citrate is ultimately going to be built up into acyl-CoA, which is going to get packaged into very low-density lipoproteins, VLDL. Everybody know VLDL? Those are the bad guys. Those are the atherogenic lipids. Remember them? Okay? And so they leak out, but there's only a little bit, because you only had 24 calories worth of glucose to start with, and most of it got metabolized. So it's just a little bit, okay? Not too much. And it'll go to your adipocyte, and your insulin will drive into your adipocyte, or it will be there, and, over time, maybe when you're 95 or 100, it might actually cause an atherosclerotic plaque. Okay, everybody got it? In addition, that insulin is going to go to your brain, okay, and acutely, remember the whole leptin thing? Acutely, it actually suppresses food intake. But chronically is the problem, not acutely. Chronically is the problem. So it's going to basically cut back on the glucose. So basically, this is a perfectly rational, reasonable energy metabolic pathway, which does not hurt the liver. Okay? Glucose is good. But fructose is not glucose. Okay? Let's talk about fructose. Fructose. You take in a soda, 120 calories, or fruit juice, let's say fruit juice, sucrose. Okay? 120 calories in an 8-ounce glass. Okay? Same as the 2 slices of white bread in terms of calories. Okay? But 100% of the fructose, which is 60 calories, the only organ in your body that can metabolize fructose is your liver. There is no other. And the reason is because the liver is the organ that detoxifies poisons. Because fructose is a poison. If fructose could be used by any other organ, then it wouldn't be a poison, but it is because only the liver can handle it. So, the 20% of the glucose of the 60 calories will also enter, right? The 80% outside. So we're really talking about 12 calories plus 60 calories. So 72 calories out of the 120 are going to hit this hepatocyte. Okay? Before it was only 24 calories, now it's 72. 3 times as much substrate to deal with. And there's the rub. Okay. So Fructose enters through this GLUT5 receptor. No other cell in the body has it. Okay? So it's just waiting. First thing that happens, fructokinase turns into fructose 1-phosphate. That depletes ATP within the cell, because there's a lot of it, right? There's a whole 60 calories worth of fructose that's going down the tubes here. That depletes inorganic phosphate. And when you deplete inorganic phosphate, you stimulate this enzyme here called AMP deaminase 1. And AMP deaminase 1 takes ADP down to uric acid. And uric acid then leaches out of the hepatocyte and rises in the bloodstream. And it turns out that uric acid blocks the neurotransmitter nitric oxide. Anybody know about nitric oxide? Nitric oxide is a muscle relaxant. So what happens if you block the muscle relaxant in the smooth blood vessels? Your blood pressure goes up. And fructose has been shown time and time again to induce hypertension, both acutely and chronically. So we ask the question, is this true in obese kids? So this is work done by Stephanie Wynn from our Peds Renal Division, okay, looking at the NHANES database from 2000. And what she looked at was here, uric acid over here against BMI, and there's a correlation. Well, that's not too surprising. Yeah, right. Okay, that's not too surprising, because after all, if you're bigger, you have more uric acid. But here's the thing. Look over here. It didn't matter. Here's obese kids over here at the 95th percentile. Here are the others. It's the same. Only the hypertensive kids have the higher uric acid. Only the hypertensive ones. And here's fructose consumption over here against uric acid, and sure enough, they correlate. So A leads to B, and B leads to C. The question is, does A lead to C? Does fructose consumption lead to hypertension in these kids? We did that. The problem is that the number of patients in that group is only about 64. It's a big, wide gap. We don't know about all the fructose they're taking in, because we only have the sugar liquids and there's other fructose. So the p-value is 0.09. We're working on it. Okay? But it's enticing. It might be. Okay? Next. So fructose 1-phosphate can go to dihydroxyacetone phosphate glyceraldehyde down to pyruvate, just like glucose could. That goes into the TCA cycle like just before. Okay? But remember, there's a bigger bolus, right? Because there's nothing stopping it. There's no regulation. There's no glycogen to put it into. In addition, these two can recombine to form fructose 1,6-bisphosphate, which can then form fructose 6-phosphate from there. And this is where the soda companies and the sports drink companies get the meat of their argument. Okay? Because fructose 6-phosphate can go back into glycogen. And it's actually been shown that if you deplete glycogen by exercise, and you give a fructose-containing beverage, you can actually replete glycogen faster. Which, of course, is what the entire sports drink movement, if you will, is all about. Okay? That's if you deplete glycogen. You name one obese kid who's got a depleted glycogen. Okay? That's a problem. Okay? That's not a good thing, that's a bad thing. Okay? Fructose 6-phosphate can then combine with glyceraldehyde to form something called xylulose 5-phosphate. And xylulose 5-phosphate, over here, as you can see, when you give sucrose, goes way up. And xylulose 5-phosphate, as it turns out, stimulates this pathway here. Stimulates something called PP2A, which then causes something called carbohydrate response element binding protein to go up. And that causes de novo lipogenesis. That causes all that citrate that comes out of there to form acyl-CoA at much higher levels than it did before with glucose. That gets packaged into VLDL. There it goes into triglyceride, into the fat cell, and of course for atherosclerosis. This just shows that if you give fructose instead of sucrose, you can see that the de novo lipogenesis goes way up. This is in humans. Okay? This is in humans also. 6 days of fructose, look at the triglyceride levels, went way up, and also the non-esterified fatty acids, the free fatty acids went up. And those are bad guys too, because they do bad things. They cause muscle insulin resistance. We're going to get there in a minute. So all of that causes dyslipidemia. Okay? Some of that acyl-CoA actually precipitates out in the fat cell as lipid droplets, causing something called hepatic steatosis. And hepatic steatosis is the beginning of non-alcoholic steatohepatitis, or NASH, which is now rampant in obese kids. Okay? We've actually had a liver transplant at UCSF in a 15-year-old from non-alcoholic steatohepatitis from soft drink consumption. Okay. I'm going to not bore you with this. It just shows that you can get a lot of fat. And this is from our clinic, 210 observations. We did univariate regression to look at beverage consumption against ALT, alanine aminotransferase, which is a marker for liver damage. And sure enough, every 120 calories, in other words, every fruit juice increases the ALT by 1 point. Okay? When we did the multivariate, it turned out insulin resistance predicted the ALT better. But nonetheless, it's there. Okay? So we're at lipid droplets, at hepatic steatosis. The free fatty acids that come out from here go to the muscle and cause muscle insulin resistance. And this is an animal study showing that this is IRS1, the substrate for the insulin receptor. As you can see, it doesn't activate as well with fructose. And PI3 kinase also does not activate as well with fructose, showing that the muscle is insulin resistant. In addition, this acyl-CoA can activate this enzyme over here called JNK1, GNK1, so does fructose 1-phosphate. And JNK1, or C-Jun N-terminal kinase 1, is what starts the inflammatory cascade, okay? Inflammation. And that takes that IRS1, which normally transduces the insulin signal, and instead of tyrosine phosphorylating it to activate it, it's serine phosphorylates it to inactivate it. So that causes hepatic insulin resistance. Okay? And I can show you that on this slide, because this is JNK1 going up with sucrose. And this is showing that with sucrose, the insulin response is muted. So you basically make your liver not work well in response to fructose. So you've got hepatic insulin resistance. Your beta cell recognizes this, has to put out extra insulin, so you get hyperinsulinemia, which actually increases your blood pressure through endothelin-1, and also ultimately causes, we also activate a little SREBP1, so you're making even more de novo lipogenesis, driving all of this fat into triglyceride for your obesity. And finally, this just shows that if you give fructose pair-fed to rats, they get very fat. And it's all fat weight. It's not lean mass. I'll get there in a minute. And finally, the last thing is that fructose, by causing insulin resistance, interferes with leptin signaling and basically makes you drink more fructose, as I showed you before. Yeah, you had a question?
Are you using interchangeably fructose in juices?
Well, sucrose is half glucose, half fructose. Okay? I don't care where the fructose comes from. It can come from sucrose, it can come from high fructose corn syrup. I don't care. It's irrelevant where it comes from.
So when you have a doctor, somebody tell you that you should be drinking pomegranate juice or cranberry juice.
Garbage. Eat a pomegranate, eat a cranberry.
Thank you.
Okay?
Can they hide fructose from you as a consumer that you don't know they're using it?
Oh yeah, all the time. All the time. Yeah. Yeah.
So when we say like a can of soda, does it matter whether it's diet or regular?
Well, diet doesn't have any fructose or glucose. I mean, it's 0 calories. Now, the big question is, do those chemicals hurt you in other ways? Okay? And that's a huge hornet's nest. Okay? I'm not prepared to talk about that today. I have loads of opinions, but I'm not really prepared to talk about that today. Personally, I think that we should all be drinking water. Okay? Okay? Water is good. Water has everything you need and nothing you don't. Okay? And it's cheap.
And minerals with the water.
Sorry.
Minerals with the water.
What minerals in water? There are minerals in water, right. There are no minerals in soda. That's right. Exactly. Okay? This is our data. Huh? Sorry.
What about carrot juice and vegetable juices?
How about carrots and vegetables? The fiber is the good part. Eat the fiber. You're throwing the fiber. You're throwing the good part in the garbage. Don't do it.
Do you know what fructose content of vegetable juices?
V8 is high.
Yes.
V8 is high. I mean, right, if you make your own vegetable juice, it's going to be low. But if you buy it processed, it's going to be high. The question is, why do they put fructose in all these things? Palatability, shelf life, and freezing.
Yes.
Why do they take fiber out of food? Because you can't freeze fiber. Go home, make a pot of brown rice, put it in a Tupperware, put it in the freezer, take it out the next day. See what you get. It might work in a shock absorber, but you wouldn't need it.
I've got friends in the French fry. You go through 14 tank cars a day.
Yeah. Well, there's a problem. Yeah, this is our data from our watch clinic looking at kids with lower insulin resistance versus higher insulin resistance. Here's higher. And look at the soft drink consumption. Okay? Our general efficacy in our patients. We do pretty well. This is how much their BMI drops over the course of 2.5 years. We are very proud of our. Okay? We think we are doing a. No one actually who publishes this stuff comes close to what we're able to do. But here's the thing you need to know. We've done an analysis of the predictors for weight loss or no weight loss in our clinic population, and front and center, the thing that inhibits weight loss the most, sugar beverage control. Okay? So now, in summary for part 2. Insulin promotes weight gain by shunning energy to fat, interfering with leptin signaling, and interfering with dopamine clearance, increasing the reward. Are insulinogenic through fructose and fiber. In particular, in food environments, been increased shelf life, depreciation, and palatability to be insulinogenic. Remove fiber, addition of fructose, which I think in and of itself explains the metabolic syndrome by itself. Nothing good will happen until we recognize, we in this room and other, shall we say, smart physicians, recognize what's going on and fix what we've done to our food supply in the name of progress. I will thank my collaborators, first at St. Jude Children's Research Hospital, University of Tennessee, Memphis, where the original studies went on, my colleagues here at UCSF and UC Berkeley in the Watch Clinic, in particular, Dr. Garber sitting here front and center, also other people who make the clinic, psychologists, lipidologists, gastroenterologists, renal people, etc. My colleagues at UC Berkeley, in particular Jean-Marc Schwartz, who is a fructose maven, who does actually clinical studies, some of the studies I showed you kids. Novartis Pharmaceuticals for supplying the free drug for the kids studies, for paying for the adult studies, that's my disclosure. And with that, I'd be happy to take any more questions. Thank you very much.
Let's take about 5 minutes.
I'm sorry it took so long.
That's all right. It was worth it. It was worth it. It was great. Thank you very much. That's it. Okay, that's it. Yeah.
Do any of the doctors study what the fluoride and the chlorine are doing, that kind of thing?
I don't know anybody who's doing that specifically, particularly with respect to obesity. Now, I know you had a talk from Bruce Ames about micronutrient intake and chronic disease. There are probably zillions of things that are going on, but I don't know if anybody who's doing that specifically.
Steve? You made a comment earlier to Phil Miller about the control of thyroid hormones involved in this. And how can you know that if you're only measuring T3 and not reverse T3?
Well, we know because T3 is regulated by TSH, and TSH is regulated by that same area of the hypothalamus. So it's a relatively good readout. Now, it would be nice to know what the reverse T3 is. I'm not saying it wouldn't, but you know that reverse T3 is basically being made by the 5-monodeiodinase type 3, which is not usually responsive to diet. It is responsive to chronic disease. So it's very hard to be able to be sure. And well, it would be nice to know. I can't answer that. I didn't do these studies.
The central mechanism affects the thyroid gland, but the conversion of T4 into either T3 or reverse T3 is a tissue level phenomenon. Therefore, it's
well, it's also there are also 3 different enzymes that do it, and it depends which tissue you're in as to which one does it, and they're not all responsive to starvation. So it's a very complicated business.
It could be part of the mechanism.
Could be. Oh, it could be. It absolutely could be. I'm not saying.
You ready? I'm hearing all these commercials recently and say, "Oh, Dad, would you buy me a little bit of diabetes?"
Yep.
And they say, "Do you feel, doctor, that these commercials are perhaps, helping?"
They're great. They're terrific. I support them completely. This has to get out into the mainstream. People have to understand what they're doing to their kids. Okay? Because government's not going to fix this. And big food certainly doesn't want to fix this.
Isn't it like tobacco? I mean, shouldn't
It's
they maybe
just like tobacco.
put a warning label on it?
I think so. I think I'm actually going to NIEHS on Sunday to give a talk on Tuesday at a workshop, and the title of the talk is Fructose is a Toxin.
One more question. Yes, ma'am.
I compare it to ethanol. Okay. Ethanol has acute and chronic effects. Fructose has no acute effects, but it has all the same chronic effects as ethanol. It's alcohol without the buzz.
First of all, Dr. Lustig he paid us to walk in with ice cream cones. I have a short comment and a short question is, I think as our society is also energetically, there's obesity is increasing, and it's like we're over excessive in our, we're wanting to eat, we're wanting to watch TV, we're wanting to have all these instant pleasures,
Right.
but we're really not full or satisfied.
Right.
And it's becoming evident in our bodies, and obesity is one major prevalence we can see so clearly, and it's sad that it's affecting the children. I work with kids, and that was my comment, and my question was, what about the artificial sweeteners, like all of the, Splendas and all that? And
someone else asked that question earlier. I'm not prepared to really talk about them. There are certain artificial sweeteners that stimulate insulin, but most don't. Okay, aspartame was the big one that I was really concerned about. Turns out aspartame does not stimulate insulin. The saccharin does.
Stevia?
Okay, saccharin does. Splenda, sucralose, does not.
Stevia.
Who?
Stevia.
Stevia, that is. I don't know what that is.
Xylitol.
Can't tell you. I don't know the answer.
Xylitol.
I know some of you have questions, so
I'm a doctor, not a
come up
medicist.
and ask Dr. Lustig after we stop. We're going to stop right now. Thank you all for coming. It's been a great show.